Okay, so today we're going to learn how to do one sample t interval, it's called. Basically, this chapter we're with means, not proportions. So that's the big change. If you know the cadence of how to do an interval, it's not that much different with means, but it is a little bit different. That's what we did with proportions. That's the old formula we used. That's the generic formula that's on your formula sheet, certainly. We would use this, except it doesn't really, we don't usually know the actual population standard deviation. So because of that, we rarely use this. I guess if they give you a mean and you know the population standard deviation, we would use that formula, but 98% of the time, we don't know that. So we're going to look at why we do what we do. So in this activity, we'll investigate the problem caused by replacing the population standard deviation, that's the Greek letter sigma, with S sub x, which is the sample standard deviation. There's a problem that happens, actually. Farmers want to estimate the mean weight in grams of all tomatoes grown on her farm. To do so, she would select a random sample of 4 tomatoes, calculate the mean weight in grams, and use the x bar to create a 99% confidence interval. Suppose the weights of all the tomatoes on the farm are approximately normally distributed with a mean of 100 and a standard deviation of 20. Use an applet to do this. Okay, so we're going to take method number 1. Let's assume we know the population standard deviation. So we're going to do that. So take a second. Okay, so we have this cool app over here. Let me kind of move this over just a touch so you can see it. Okay. So I'm going to fill out the drop downs there. The first thing we're going to do is means instead of proportions. It is normal. We're going to do z with sigma. We're going to say the population was, the mean was 100. The standard deviation was 20, I believe. Sample size was 4. We're just going to take one interval, but we need to do this at the 99% confidence interval level. So I took one. You can see that green line right there, that horizontal line. It does seem to capture the true mean of 100. I'm going to take another sample. That green line changed slightly. You can see the green line keeps, I'm sampling many different individual intervals, and all of them so far have contained the true mean. In fact, we would expect 99% of the confidence intervals created would. So I'm going to do this. I'm going to create 100 at a time. So I'm going to add another 100 to this. Oh, there's 100 of them. One of them out of 100, that red line up there, if you see it, does not contain the true mean of 100. I take another 100. Another time, one of them did not contain the true mean. Another one does not contain it. Well, we're very close to, so you can see after 500, well, let me go a few more. There's 1,000-ish. So 99.1% of the time, we have captured the true interval. That seems about right. We expected 99%. We got 99.1. This is a good way to do it. If for some reason you actually know the standard deviation, have at it. We don't ever know that though. So let's try what we thought was the next best thing. We're just going to take the standard deviation of the sample, use that. Should be good enough, right? So I'm going to reset or recalculate here. Take a sample of 100 of them. Okay, I got 2 of them. That's not bad. That's pretty good. Ooh, I got a few more. That 100. Ooh, I got a few more. Ooh, let me take about 1,000 here to see what happens. Okay, there's 1,000. 94% of the time, we captured the mean in our intervals. 94% of the intervals. That's not so good. We wanted 99. 94 seems not very good. So we've got to be something better. So a guy from a company called Guinness Beer, might have been Ireland, but anyway, he was a statistician and he was taking samples and he noticed what we just noticed. He's like, that's not accurate. He was taking samples of his beer and they weren't coming out. The intervals were not coming out like he wanted them to. So he came up with a whole different kind of distribution. It's called the t-interval. I'm going to show you that here. So the t-interval is different and it should, let's recalculate, and I'm going to take like 1,000 of these guys. 98.6 is pretty close to 99%. You can see the t-interval works a lot better. Even though we don't know the population standard deviation, if we use the t-curve, it kind of works. So this guy was brilliant. He came up with a plan because that second plan is not that plan. Is method number 2 is terrible because you got like 94%. That wasn't close at all. And so we can use the t critical value to get this. So this is what the t curve looks like. The blue line is what we're used to. That's the standard normal z distribution. The green line has thicker tails. It's much wider, so it has more variation. But it's a better predictor than the z curve for a small sample size. As your sample size grows, especially it gets closer to 30 or more, it starts to look an awful lot like the z curve there. So it gets more and more normal as the sample size grows. In fact, this is a pretty good definition there. Do you see that red line? That's degree. That's when you have a sample size of 3. When you have a sample size of 10, it almost starts looking pretty close to normal there. So a couple things on this page I want you to see. Instead of z critical value, we have to find the t critical value. And write down degrees of freedom equals n minus 1. That's a formula. That's a thing that a lot of students just forget to write on their paper when they do a problem. So how do you find this? So it's similar to finding z critical value. So if you've done that with z critical value, this won't be much different. So let's draw a 95% confidence interval. So there'd be 2.5% to each side. So we're finding this value. This is called the t star or t critical value. It's a star there if you didn't see that. T critical value there. So instead of using the old inverse norm, that was the command we used to use, we're going to use the inverse t command. The area to the left of that t critical value is 97.5, so 0.975. And there's one other thing you have to put. You have to put the degrees of freedom here. So because on this one, sample size n equals 12, we're going to say the degrees of freedom is 11. So n minus 1 is the formula for degrees of freedom. So you get your calculator out, and we're going to type that guy in there. So I hit menu, 6, I think it's 5. And you can see we're actually, instead of, these are the two we're used to, norm CDF and inverse norm. Now it's TCDF for means, and what we're going to use right now, which is inverse T. So we're going to go to inverse T, 0.975, and then 12 minus 1 is 11. So we should get 2.2. So 2.2 is the correct answer for the T critical value. Try to find that next one there. Try to find the 90% with 48 observations. So you would just, your calculator show areas 0.95 because you have 5% to the left and the 90%. And degrees of freedom is n minus 1, so it'll be 48 minus 1, which is 47. Type in inverse T in your calculator and you get that answer. Okay, conditions are basically pretty similar. First one's exactly the same. Random condition, looking for a random sample. I guess it's experiment, random sampling. Less than 10% condition, we want to sample less than 10% without replacement. And then large sample condition. We used to call this large counts, but for means it's called large sample. And this is the breakdown of the large sample condition. There's 3 ways to prove it. Maybe the population is normal, then your sampling distribution is normal. Maybe your sample size is large enough. If n is at least 30, you're good to go. If the sample size is small and they give you the data, you might have to draw the data. We're looking for something that maybe looks approximately symmetric, although we're kind of loosey-goosey with that, but definitely no strong skewness to either side or outliers. It's what we don't want. So for example, let's check the large sample condition. To estimate the GPA of students at your school, you randomly select 50 students. Here's the histogram. So can we prove this is approximately normal or fits the large sample condition? Because the sample size of 50 is greater than 30, we can definitely do that and say that's the reason. I think you also could have drawn that or pointed to that graph and said, no, there's not strong skewness, no major outliers there. We could say this data is going to be approximately normal. Second case, does large sample fit here? How much force does it take to pull the wood apart? Snapshot shows the force in pounds required to pull a piece of Douglas fir apart for each of 20 randomly selected pieces. Okay, and if you look at, we don't know the population. N is not large enough. If you turn that stem plot aside, you can see it's skewed left pretty badly. That's not going to work. No, not good. This one, we don't know the population, and it's smaller than 30. But if you look at the graph, it's not too bad. It's only mildly skewed. So I think you could actually say this one's okay. You draw a picture of the stem plot if it's not already there as your reason or your proof that this is not majorly skewed. Go ahead and definitely, if they ask you to do an interval, don't stop because you think a condition is wrong. Keep going. Usually, if there is a condition wrong, they'll ask that as a separate part of the question, which happens sometimes. Okay, so let's try this one. So this is actually our formula. You want to write that down in your notes for how to conduct a confidence interval. So in this case, you might be familiar with this example. 73% of Americans claim they've read a book. The average number of books read in a year is 12. Standard deviation is 18. So there's a lot of variation there. Construct and interpret a 95% confidence interval. So the first thing you would do for this one is to define the proportion, or the mean, I should say the mean. The mean, the mu, that's a Greek letter mu, the true mean of, and then just talk in context, of all Americans who have read books in the last year, right? So define that. The confidence level is 95%. So I think that would be the first, the state stuff. Okay. So now plan. The name of the test is called a one sample t interval. You would check the conditions X. So random sample, I like to underline that in the paragraph and then write the words random sample with the arrow to that. Less than 10%, 1520 is certainly less than 10% of all Americans. And is the sample size large enough? Oh my goodness. 1520 is greater than or equal to 30. So yes, that works if you want to see that. Those are the three conditions that were tested there. So those all work. Okay? Okay, so now, and by the way, it's called a one sample t interval if you didn't catch that. So now we're going to plug into that formula there. So X bar, so I would recommend writing in the numbers here when you do this. So X bar is 12 plus or minus the t critical value. So we have to find that. So you would get your calculator out and go, okay. So let's go back to inverse norm. So I don't think we found it yet for this one. Many 6, 5, inverse t, I should say. Inverse t is 6. Area's point for 95 is 0.975. Degrees of freedom, 1519, I believe. 1520 minus 1. Okay, 1.96. That actually makes sense, right? Because if the sample size is really large, it looks very normal. And that's the number, if it was a Z-curve, it would be exactly that. I think this is the number 18 is the sample standard deviation divided by square root of n, so square root of 1520. What I would do now is do this in your calculator. So go to menu, 6, confidence interval 6, and then t interval is 2. So choose stats, we'll do data tomorrow. This is 12, 18, n was 15, 20, and 95%. So it gives you a bunch of stuff. So I'm going to write down 12 plus or minus the margin of error, because these two guys together are the margin of error. So this would be 0.905 is what it says, or 906. And then the upper bound and lower bound, I think the lower bound was 11.09, and then 12.9 or 12.13 there. So interpret it. We are 95% confident. The true interval, the interval from 11.09 to 12.9 contains the true mean amount of books that an American has read in the last year. The last question does say this. It's kind of a follow-up. It asks about, let me get this. So part B, in the Pew report, they said adults read 14 books. Well, according to our interval, which was 11 point something to 12 point something, 14 isn't in our interval. So we don't have enough evidence. In fact, we have evidence to say, because 14 is not in our interval, it's not a plausible value, which means we don't think this new research or the old research, whatever it is accurate here. That's your lesson for today. Tomorrow we'll learn about